Dennis Oberholzer sits at his desk in Lockheed's Burbank facility, spring 1975, staring at a mimeographed translation of a Soviet physics paper. The pages are covered in integral equations predicting how radar waves scatter from metal edges. His task is to calculate whether a diamond-shaped aircraft built from flat triangular panels can become invisible to enemy radar. No wind tunnel can answer that question. No existing computer code can handle conventional airframe geometry. If the Soviet mathematician's theory is wrong, the entire stealth prototype will light up radar screens like a highway billboard. The Air Force will cancel the program, and Lockheed will lose the contract. Oberholzer has no backup plan and no second theory to fall back on. 13 years earlier, Soviet physicist Pyotr Ufimtsev had published a paper in a Moscow technical journal titled Method of Edge Waves. He presented a new way to predict radar reflections by calculating electromagnetic currents traveling along the edges and discontinuities of a metal surface. The integrals were exact solutions to Maxwell's equations for simple geometric shapes. Peer reviewers confirmed the math was correct, and the paper circulated through Soviet radar research institutes. But no one saw a way to use it for real aircraft. Soviet radar engineers acknowledged Ufimtsev's edge-wave method worked for flat plates and simple corners, but they saw no practical application. Aircraft were curved, complex, and built for aerodynamic performance. The equations required braking surfaces into basic geometric shapes, and no one believed a real airplane could be designed that way. Aviation design bureaus at Mikoyan and Sukhoi prioritize speed, climb rate, and maneuverability. They dismissed edge-wave theory as abstract mathematics with no utility for airframe development. Ufimtsev's paper circulated in Soviet technical libraries for the next decade, generating no follow-up research and no prototype funding. The physicist moved on to other projects. Meanwhile, the U.S. Air Force Foreign Technology Division in Dayton, Ohio, translated thousands of Soviet technical papers each year as part of routine intelligence collection. Ufimtsev's edge-wave paper was translated into English in 1971 and filed in the Defense Technical Information Center archive. It sat there, unread by most American aerospace engineers. By 1975, the Pentagon had watched Soviet-built air defense networks shoot down American and Allied strike aircraft over Vietnam, the Sinai, and the Golan Heights. Surface-to-air missiles guided by ground radars were proving more effective than speed or jamming alone could defeat. DARPA launched a competition for a stealth technology demonstrator, inviting proposals from defense contractors. The requirement was simple: build an aircraft that enemy radars cannot detect in time to engage. Existing radar cross-section analysis relied on a technique called method of moments, which solved Maxwell's equations across an entire aircraft surface. For simple shapes like spheres or flat plates, the calculations were manageable. But a real fighter jet with wings, tail, engine inlets, and fuselage required solving thousands of simultaneous equations. The mainframe computers available in 1975 could take weeks or months to analyze a single complex airframe, making iterative design impossible. Lockheed Skunk Works and Northrop both submitted proposals for the DARPA demonstrator. Northrop engineers favored smooth, curved surfaces, believing gradual contours would scatter radar energy gently and reduce returns. The approach matched traditional aerodynamic design and looked like a fighter. Lockheed had no illusions about solving the full three-dimensional problem. If they couldn't compute the answer, they would have to simplify the geometry so drastically that the equations became tractable. Dennis Oberholzer, a Lockheed mathematician, spent weeks searching the Defense Technical Information Center archive for alternative radar prediction methods. He found Ufimtsev's translated edge-wave paper filed under electromagnetic scattering theory. The integrals looked solvable for flat panels because each facet could be treated independently and the results summed. Curves remained impossible. The radius changed continuously, and the edge currents became unpredictable. Oberholzer realized he could design an aircraft from flat triangles only, accepting any aerodynamic penalty to make the math work. Oberholzer drafted a memo proposing a faceted aircraft built entirely from flat triangular panels, arranged to deflect radar energy away from the transmitter. Every surface would be a simple plane with sharp edges. The design would abandon smooth aerodynamic contours, but the radar cross-section could be predicted using Ufimtsev's edge-wave integrals on a 1970s mainframe in hours instead of months. He called the approach physically ugly but mathematically tractable. Skunkworks director Ben Rich read the memo and authorized a proof-of-concept analysis. Overholser began coding a Fortran program he named Echo 1. The software divided an aircraft surface into flat facets, calculated the edge-wave contribution from each panel using Ufimtsev's integrals, and summed the scattered radar power for any given angle of illumination. Each facet was treated as an independent reflector with predictable specular behavior. The code ran on Lockheed's IBM mainframe and output a radar cross-section plot in a few hours. Early test runs on simple shapes validated the method. Overholser tested Echo 1 against simple targets with known radar signatures: a flat metal plate, a dihedral corner reflector, and a trihedral. The code's predictions matched laboratory measurements within acceptable margins. The Soviet mathematician's edge-wave integrals held up under scrutiny. Now the question shifted from whether the math worked to whether an actual aircraft could be built from flat facets and still fly. Ben Rich convened a design review and told the team to proceed with the faceted approach. Lockheed's design team arranged flat panels to form a diamond-shaped planform with sharp chines, faceted sides, and a flat underside. Every surface was a plane. There were no curves anywhere on the airframe. The shape deflected radar energy in narrow specular lobes, steering returns away from the direction of the transmitter. Engineers nicknamed the configuration Hopeless Diamond because it resembled a child's paper airplane and violated every principle of streamlined aerodynamic design. Program manager Alan Brown accepted the aesthetic penalty and moved forward. Scale models went into the wind tunnel at Lockheed's facility. The results confirmed the worst predictions. The faceted airframe generated asymmetric airflow, early boundary layer separation, and unpredictable pressure distributions. The aircraft was unstable in pitch, meaning it wanted to nose up or down without pilot input. It was unstable in roll, tending to bank uncontrollably. It was unstable in yaw, meaning it would weather vane in turbulence. No human pilot could correct all three axes fast enough to maintain controlled flight. Alan Brown made the decision. The aircraft would rely entirely on a computerized, fly-by-wire control system with no mechanical backup. Sensors would measure airspeed, angle of attack, and angular rates dozens of times per second. The computer would calculate corrective control surface deflections and actuate them faster than a human could react. The pilot would input desired maneuvers, but the computer would do the flying. If the control system failed, the aircraft would depart controlled flight in seconds. Brown signed off, trading human control for stealth. Radar cross-section measures how much radio energy an object reflects back toward the transmitter. A conventional fighter scatters radar waves in many directions. Some energy inevitably returns to the enemy antenna. The larger the return, the earlier the radar detects the aircraft, and the more accurately it can track position and velocity. Reducing radar cross-section means steering reflected energy away from the transmitter, making the aircraft appear smaller or even invisible on the scope. Ufimtsev's method calculates electromagnetic edge currents, waves that travel along surface discontinuities, like panel edges, seams, and corners. When a radar wave hits a metal surface, it induces currents in the material. Those currents re-radiate electromagnetic energy. For flat facets, the edge currents follow predictable paths along the straight boundaries. Ufimtsev derived integral equations that sum the contributions from all edges to find the total scattered power in any direction. The integrals are solvable for simple geometric shapes using 1970s computers. Flat facets reflect radar energy like mirrors reflect light, in a narrow specular lobe determined by the panel's angle. If the facet is tilted away from the radar, the reflected energy bounces off into empty space rather than back toward the antenna. By arranging multiple flat panels at carefully chosen angles, Lockheed's designers could ensure that no matter where the radar looked from, at least most facets would deflect their returns away from the threat. The result was a dramatically reduced average radar cross-section. Curved surfaces concentrate edge currents unpredictably because the radius of curvature changes continuously along the surface. Ufimtsev's integrals require defining discrete edge boundaries. A smooth curve has infinitely many tangent points and no clean edges. Solving the equations for a curved wing or fuselage would require subdividing the surface into thousands of infinitesimal elements, far exceeding the memory and processing speed of 1970s mainframes. Lockheed had to use flat panels not by choice, but by computational necessity. The faceted airframe's sharp chines and abrupt angles forced boundary layers to separate early, reducing lift and increasing drag compared to smooth designs. The flat underside and angular cross-section created asymmetric pressure distributions that shifted unpredictably with speed and angle of attack. Each facet generated its own local flow field, and where facets met, vortices formed that destabilized the aircraft. The shape was optimized for radar invisibility, not for staying in the air. Pitch instability arose because the center of pressure moved forward and aft with angle of attack, creating moments the horizontal tail could not counteract passively. Roll instability came from asymmetric lift on the faceted wings. Any bank angle increased itself rather than self-correcting. Yaw instability resulted from the flat sides acting like vertical sails in crosswinds or sideslip, amplifying any heading deviation. A human pilot would input corrections too slowly. The aircraft would diverge from controlled flight in under 2 seconds. The fly-by-wire system read sensor data from gyroscopes, accelerometers, and air data probes dozens of times per second. The computer compared actual motion to the pilot's commanded flight path and calculated the control surface deflections needed to correct the difference. Electric actuators moved the elevons, rudders, and stabilizers within milliseconds. The computer masked the inherent instability by making constant micro-corrections, faster than a human could perceive. As long as the control loop ran without interruption, the aircraft flew as if it were stable. April 1977, Lockheed towed the Have Blue prototype onto the radar cross-section test range at Area 51 in Nevada. The aircraft sat on a pylon under open sky, surrounded by target-tracking radar arrays positioned at multiple angles. Engineers had no backup plan. If Echo 1's predictions were wrong and the facets scattered energy unpredictably, the entire program would collapse. The Air Force would cancel the contract, and Lockheed would lose the stealth competition to Northrop. Ben Rich and Alan Brown watched from the control trailer. The test crew activated the first radar array, illuminating the prototype from head-on aspect. Operators monitored the return signal strength on oscilloscope displays and recorded data on magnetic tape. The first readings were so weak that the radar operators checked their equipment, assuming a malfunction or calibration error. They recalibrated the antennas and repeated the measurement. The return remained barely above the noise floor. The faceted diamond was scattering almost no energy back toward the transmitter. Engineers rotated the pylon and tested side, oblique, and tail-on aspects. At a few specific angles, narrow spikes appeared when a facet aligned perfectly with the radar beam and reflected a strong return. Those spikes matched Echo 1's predictions exactly. At every other angle, the return stayed below detection thresholds. The average radar cross-section across all aspects was orders of magnitude smaller than any operational fighter. On enemy radar screens, Have Blue would appear as background clutter or a bird. Ben Rich and Alan Brown stood in the control trailer watching the data stream in. The Soviet physicist edge wave theory, dismissed by his own government, had just made an American aircraft nearly invisible to radar. Ufimtsev's integrals, translated in 1971 and filed away in an archive, had proven accurate enough to design a real stealth prototype. Lockheed had trusted foreign math and accepted a shape that violated every aerodynamic instinct, and the gamble had paid off. Within weeks, the Pentagon reviewed the radar range data and awarded Lockheed the full-scale development contract. Northrop's curved design had failed to achieve comparable reductions in radar cross-section because the smooth contours could not be accurately predicted with existing tools. The faceted approach won the competition. The Air Force committed funding for an operational stealth strike aircraft designated F-117, based directly on HAV Blue's flat panel geometry and fly-by-wire control architecture. HAV Blue flew for the first time in December 1977. Test pilot Hal Farley took the prototype airborne from Groom Lake and confirmed that the fly-by-wire system could mask the 3-axis instability. The computer made dozens of control corrections per second, invisible to the pilot. Farley reported the aircraft handled predictably, despite its bizarre shape. The flight proved that a faceted stealth design, though aerodynamically unstable, could be safely operated with electronic control augmentation. The Air Force began redesigning strike doctrine around undetected penetration instead of high-speed dashes through defended airspace. If an aircraft could evade radar detection, it did not need supersonic speed or dogfight agility. Stealth allowed subsonic, non-maneuverable attack jets to operate in hostile environments that would destroy conventional fighters. The F-117 became the first operational aircraft built on this principle, entering service in 1983 under strict classification. As computer power increased through the 1980s, Lockheed engineers expanded Echo 1 into more sophisticated radar prediction codes. Eventually, processors could handle the computational load for limited curved surfaces, allowing later stealth designs like the B-2 bomber and F-22 fighter to blend facets with smooth contours. But the foundation remained: Ufimtsev's edge-wave integrals, validated by HAV Blue's flat panel gamble in 1977. The F-117 proved the stealth concept in combat during the 1991 Gulf War. The jet struck heavily defended targets in Baghdad on the first night of the air campaign, encountering dense surface-to-air missile coverage and integrated air defense networks. Iraqi radars could not track the faceted aircraft reliably enough to guide interceptors or missiles. The F-117 fleet completed the war without losses, validating the operational value of radar invisibility. In the early 1990s, after the Cold War ended and the F-117 was publicly revealed, Pyotr Ufimtsev learned that his 1962 edge wave theory had enabled American stealth aircraft. Western aerospace journals interviewed him, and he expressed surprise that anyone had built hardware from his abstract math. Soviet aviation bureaus had never tested his equations on real airframes. They published the blueprint for radar invisibility, then filed it away and forgot it for 2 decades. If Soviet aviation design bureaus had funded applications of Ufimtsev's theory in the 1960s or 1970s, they could have developed stealth aircraft a decade before the United States. The math was correct, published openly, and available to any engineer in the Soviet technical library system. Instead, they prioritized speed and maneuverability, dismissing edge-wave scattering as impractical. The Soviets handed America a strategic blueprint and never realized what they had given away. Lockheed's success came from trusting a Soviet physicist's equations no one else believed in. Oberholzer, Rich, and Brown accepted career-ending risk by building a prototype from untested foreign theory and a shape that defied aerodynamic common sense. They chose mathematical tractability over aesthetic design, flat panels over curves, and electronic stability over natural flight characteristics. That willingness to follow the math, regardless of origin or appearance, created a new class of aircraft. The faceted design, born from 1970s computational limits, became the foundation of modern stealth technology. Later aircraft refined the geometry, but all relied on Ufimtsev's edge-wave method to predict radar returns. The F-117 retired in 2008, but its design philosophy, trading aerodynamic performance for electromagnetic invisibility, persists in every stealth platform flying today. The Hopeless Diamond proved that the right constraint, accepted fully, can unlock capabilities no one thought possible. Pyotr Ufimtsev's 1962 paper was correct, elegant, and available to anyone who looked for it. The Soviet Union published it, classified it as unimportant, and moved on. The United States translated it, filed it in an archive, and nearly ignored it. One Lockheed engineer found it, trusted it, and built an invisible jet from its equations. The story of stealth is not about secrecy or espionage. It is about recognizing the value of an idea everyone else dismissed. By the mid-1970s, the Pentagon knew that radar-guided surface-to-air missiles were downing strike aircraft faster than jamming technology could counter. Every mission over defended territory became a calculated gamble. Fly fast and hope the radar tracking window stayed narrow, or fly low and risk ground fire. Stealth offered a third option: become undetectable. But no one knew how to design an aircraft that radar could not see. The Air Force Foreign Technology Division in Dayton processed thousands of Soviet technical papers each year, translating anything that might offer intelligence value. Ufimtsev's Edgewave paper arrived in 1971, was translated by a contract linguist, and entered the Defense Technical Information Center catalog. The abstract mentioned radar scattering and electromagnetic theory, but nothing flagged it as urgent. It sat in the archive for 4 years, available to anyone with a security clearance and a reason to look. Overholzer wrote Echo 1 in Fortran because the language could handle matrix operations and iterative summations efficiently on IBM mainframes. Each facet became a matrix element, each radar angle a loop iteration. The code was less than 1,000 lines, simple by aerospace standards, but it was the only tool that could predict radar returns from a faceted shape in practical time. If the code contained a bug or a misunderstood integral, the entire stealth program would fail at the radar range. For 2 decades, the Air Force had built fighters and attack jets around speed and agility. Doctrine assumed that a fast aircraft could penetrate defenses before radars locked on and missiles launched. The F-4 Phantom, F-111, and F-15 all prioritized speed, thrust, and maneuverability. Proposing a subsonic, non-agile attack jet contradicted every lesson the service had internalized since Korea. Ben Rich had to convince Pentagon leadership that invisibility could replace performance. When engineers compiled the full radar cross-section dataset from all test angles, they calculated an average return smaller than a large bird. Conventional fighters of the era showed radar cross-sections measured in square meters. Have blue measured in fractions of a square meter. The faceted design had reduced detectability by more than an order of magnitude. Enemy radars would see noise, clutter, or nothing at all until the aircraft was overhead. Hal Farley flew dozens of Have Blue test missions, pushing the flight envelope to confirm the fly-by-wire system could handle turbulence, high-G maneuvers, and asymmetric flight conditions. The computer never faltered. Control laws updated fast enough to mask the instability, even when Farley deliberately provoked departures. The success of those flights removed the last institutional objection to the faceted stealth design and cleared the F-117 for production. The Air Force ordered full-scale production in 1978, committing to 59 operational F-117 Nighthawks. Lockheed built them in Burbank under strict security, using the same flat facet geometry and fly-by-wire architecture proven by Have Blue. The jets entered service at Tonopah Test Range in Nevada in 1983, operating under classification for 5 years. Pilots trained at night to keep the shape secret. The program remained hidden because the Pentagon knew the Soviets would copy it the moment they saw it. Pyotr Ufimtsev's Edgewave integrals, published in Moscow in 1962, enabled a class of aircraft that redefined air warfare. Soviet aviation bureaus read the paper and saw no application. American engineers read the same paper and built the F-117, the B-2, and every stealth platform that followed. The difference was not in the math or the translation. It was in the willingness to trust a theory that contradicted every design instinct and accept constraints that looked like failures. Stealth did not come from secrecy. It came from reading the book everyone else ignored.